Your base, yes. Okay. So finally, we get to the Schwarz Lemma. Okay, so all the video clips I've given for Spaceballs, if you haven't seen Spaceballs, it is a great movie. I highly recommend it. It will sadly not help you too much in this class. Okay, so there's 3 parts to the Schwarz Lemma. And so we're going to let F be a mapping from the unit disk to the unit disk. It's going to be holomorphic. I think we will normalize it so F sends 0 to 0. It's not a big deal to assume that F sends 0 to 0. Remember, we had our functions C alpha from last time, which were their own inverse. And so we can and these map the unit disk to the unit disk. So if I have a holomorphic map from the disk to the disk that doesn't send 0 to 0, I can just say, well look, 0 had to go somewhere. Let's say 0 went to alpha. I'll now compose my function with C alpha, and now I have a new function which maps the origin to the origin. So it's not a big deal to do something like this. If you've taken probability, you've heard about standardizing random variables. So you're comparing apples and apples. Now I want things to have maybe mean 0, variance 1. That's essentially the game we're playing here. Why not just make life good and assume 0 is sent to 0? Okay, so the first statement, I want to get them in the right order, is the absolute value of f of z is less than or equal to the absolute value of z. The second is if there exists a z0 such that the absolute value of z0 equals the absolute value of z0 with z0 inside the unit disk, then what we have is f is a rotation. And the last one is the following. F prime of 0 is less than or equal to 1 if it equals 1, then we have again f is a rotation. Okay. So when you have something like this, the first thing you should do is you should check. Can you give me any functions that are holomorphic from the unit disk to the unit disk that map 0 to 0? The identity. I was actually expecting Philippe to yell that out fast.
I was like literally about to.
I know, I was about to say you beat Philippe very good. So I will leave it to you to check that this holds trivially if we have the identity. Okay? Can you give me another function from the unit disk to the unit disk?
5z.
I'm sorry?
5z.
5z. That's not going to map the unit disk to the unit disk. So correct it. Change where you put the 5. Instead of doing 5z, do what? Z to the 5th. Or z over 5. Right? So, example, z over 5. And if I do that, I'm never going to have a z inside the unit disk. Okay, so I guess we should put a little extra restriction on the z0. Where we say f of z0 is equal to the absolute value of z0. What restriction do I want to put in? Because this function does have a point z0.
Isn't that rotation? Isn't that a rotation?
No, it's not a rotation, it's a dilation. I want z0 not to be 0. There's a point other than 0. Because this is trivially going to be true because I'm assuming f of 0 is 0. So z0 not. Okay? So z to the 5th is another example that would work. And what you can see is, if I'm inside the unit circle, z to the 5th is going to have smaller magnitude. Okay. What about its derivative? So its derivative, f prime of z, is 5z to the 5th. So do you believe the Schwarz Lemma? supposed to have read the Schwarz Lemma. You're supposed to know it. Do you believe the Schwarz Lemma? Does this pass the test? It does? All happy?
No. Isn't the magnitude of f of z... Oh no, it is smaller, yeah.
It's smaller.
Yeah.
Yep, because this is going to be smaller in value, and what's the derivative at 0?
0.
Which is less than 1. Okay. So far, the Schwarz Lemma seems to be passing all of our tests. We were a little careless, we forgot z naught naught naught. Other than that, seems to be good. Can you give me any other maps from the unit disk to the unit disk?
C e to the I gamma.
Sure. I'm going to write it this way. E to the I theta times z, which is a rotation. And so, good. In fact, we have lots of places where the absolute value of f of z naught is the absolute value of z naught, and f is a rotation. And the first derivative at 0 does equal 1 in absolute value, and it's a rotation. Good. So far, every case we've looked at, the Schwarz Lemma has held. Okay? So we have two options. We can prove the Schwarz Lemma now, and then discuss the real case, or we can try to look at the real case first, and then just try to prove the Schwarz Lemma. Whoever speaks first wins.
Let's look at the real case.
Alright, let's look at the real case. So we've just done a lot of tests about the Schwarz Lemma in the complex case. Let's see what would hold in the real case. Now again, our function is holomorphic, so to be fair, I should require my function to be, at the very least, differentiable in the real case. Maybe real analytic, maybe it's given by a Taylor series expansion. What's the analog of the unit disk on the line? The unit interval. Well, not the unit interval. So, real case. So we have -1 to 1. So I want to find maps from -1, 1 to -1 to 1. Can you give me a map that does that? Identity. Okay, identity works, and these things, okay. What else? X to the 5th works. And so we could try x to the 5th, and if we do x to the 5th, we're going to have exactly the same results as before. Anything else? Negative x to the 5th? Or
Just x to the 4th?
X to the 4th would not work.
Yeah.
Well, okay, I'm sorry. I didn't say it had to be onto, I just said it had to be into. So x to the 4th would work. So x to the 4th would work too. Negative x would work. And now what's nice about x to the 5th and negative x is these are all 1-to-1 onto functions. So can you think of another 1-to-1 onto function? So one of the big statements in the Schwarz Lemma is that the absolute value of the derivative at 0 is at most 1. So the question is that true also in the real case? If I have a map from -1, 1 to -1, 1, let's say it's onto, let's say it's real analytic, so I have a real analytic isomorphism between these two, must the first derivative be at most 1 at the origin? So can you give me a function?
I can draw you a function.
I want a name for the function. It's a name you've all heard. So what's good functions to try? So arctangent is 1 over 1 plus, I'm sorry, arctangent works. Arctangent is a very good one. So we're going to have to fix it up a little bit.
Yeah.
Alright, so the idea was to try something like arctan. Now what's arctangent of 1? So arctangent of 1 is pi over 4. So what else should I multiply this by? 4 over pi. And arctangent of minus 1 will be minus pi over 4. So this will map minus 1, 1 to minus 1, 1. It's infinitely differentiable. It's given by its Taylor series expansion. And now let's see what's the derivative. The moment of truth. Do you think for once real analysis can win? What do you think?
Didn't you win that other
Yeah.
time?
Which other time?
Second time.
Wait, when did it win?
Never happens.
When did it win?
Definitely won before.
I thought it won when we were talking about it might win here.
No.
No? Okay.
It loses.
It loses? Let's calculate the derivative. So the derivative is 4 over pi, and the derivative of arctangent is 1 over 1 plus x squared. Right? So what's f prime of 0?
4 over 5. Bigger than 1.
Real analysis wins. Right? Unquestionably, real analysis wins here.
Definitely won.
Okay? I will, please email me the other time one. So we got f prime of 0 is 4 over pi. If you look at some state and local legislatures, people have sometimes created laws as to the value of pi. Some places have declared pi to be 4.
Wow.
Yes.
No, wait, what?
Oh, there are places that have declared pi to be 4. There's places that have declared pi to be 3. What this means is you want to buy areas in circular lots and sell them in square lots or vice versa, depending on how they define pi.
That would be awesome.
But we will assume that we are not in a place where pi has been declared to be 4. Pi is still approximately 3.14. So this is a victory. There's another nice trig function that we could use to go from -1, 1 to -1, 1. Yes?
Why is this a victory? Doesn't it mean it fails the lemma?
Doesn't match, so it doesn't meet the third condition.
I mean, I'm looking at this as, I don't know. I guess it's point of view. I guess I'm just so tired of real analysis losing. I'm calling it a victory that it can have a larger derivative. But I guess you could say that, I guess, before what we were saying with, bounded holomorphic function that's entire has to be constant. Then you could say it's a victory for real, and I guess you're right. We really shouldn't call this a victory for real analysis. We should say that it's too wild again. Wild and unrestrained. Function's gone wild, okay. Now the question is, there's a natural question you can ask now.
So what's the new restriction on the derivative?
What's the new restriction on the derivative? How large can it get? So can anybody give me another nice function? It's another trig function that I could use to map -1, 1 to -1, 1. Let's take the sine of x. And we've got to be a little bit careful. What's the sine of 1? What do we, when x equals 1, we want to take the sine of what quantity? We need to multiply x by something. What should we multiply x by? Pi over 2. And now this will map -1, 1 to -1, 1. So we take its derivative, we get g prime of x. Derivative of sine is cosine of x. And now we have an extra factor pi halves coming out.
So have the pi over 2 inside.
Oh, you just have a pi over 2 inside. And so g prime of 0 is now just pi over 2. So which would you rather have, 4 over pi or pi over 2?
Pi over 2.
Why pi over 2? So if I compare 4 over pi versus pi over 2, that's 8 versus pi squared. Right? I don't want to actually do any significant algebra. I'd much rather have pi squared versus 8. It's larger this way, it's larger this way. Pi over 2 is better than 4 over pi. So, first, Pat gave us 4 over pi. Looking at sine, we've increased it all the way up to pi over 2. How far do you think you can push this? How far is very far?
very, very particular.
So when I taught this class a few years ago, one of my students and I were curious as to how far could you push this. And we showed you can make the derivative arbitrarily large at the origin. You can get it as close to infinity as you want. Very, very different than what goes on in the complex case. And you can do this while at the same time preserving the equivalence to an infinite differentiable function whose Taylor series equals that function. So, once again, the real analysis case is very different than the complex. And I think you're right, I should not be calling this a victory for real analysis. This is yet another defeat of real analysis at the hands of complex.
Can't you do that with a complex function too? It just won't be a rotation.
Okay, so give me a complex function that maps the disk to the disk, is holomorphic, is 0 at 0, and its first derivative is larger than 0 at 1. I mean, is larger than 1 at 0.
Doesn't Schwarz's lemma not prove that you can't do that though?
Well, Schwarz's lemma is telling us that if I have a holomorphic map from the disk to the disk that's 0 at 0, then its first derivative is at most 1 at the origin. So Schwarz's lemma is telling us that in the complex case, we can't have a derivative greater than 1 if we have this conformal mapping. So the Schwarz lemma is really restricting the behavior of the function at the origin. So I'm going to give two proofs of that last statement. One from the book, one that's not quite in the book but is using the same beginning. Alright, so this is where we're going to start to use a lot of our results from maximum modulus principle and Boucher's theorem and all that stuff, open mapping theorem. These are going to be necessary inputs to getting to the Riemann mapping theorem. So, proof of Schwarz 1. Okay, so we want to show that the absolute value of f of z is less than equal to the absolute value of z, and we know f of 0 is 0, f from d to d is holomorphic. Well, instead of looking at f of z is less than equal to the absolute value of z, what's a nice way of rewriting that? So how could I rewrite that expression?
f of z minus z is less than 0.
I can't do that because I have absolute values. I have to have absolute value of f of z minus the absolute value of z. I'm sorry?
Can you do that? Does that work?
It could work, but then you would have a difference of absolute values, and the difference of absolute values is not going to be easy to work with. Because remember, absolute values are not holomorphic. So what's a good expression I could look at that's related to f of z less than or equal to z in absolute value? And remember, you know f of 0 is 0. Alright, who are my physicists? What are you not allowed to do in physics? Well, I'm sorry, what are you allowed to do in physics that you can't do in math without justification? Divide by 0. So that's a hint. What should we study?
f of z over z.
F of z over z. So we'll study g of z is f of z over z. Is this a legitimate thing to study? Yes, because f of 0 is 0, this is well defined. It's a removable singularity. So removable singularity as f of 0 equals 0. Okay, do you know any way to study the magnitude of a function? Where is a function large? But this function doesn't have any poles. So this function is holomorphic. So g is holomorphic. So how can you figure out where a holomorphic function is large? On the boundary. So we have two different boundaries we could look at. We could look at, say, absolute value of z is equal to r, or we could look at the absolute value of z equals 1. And so let's study g of z on a circle of radius 0 less than r less than 1. I'm trying to think. The book likes to go through a circle of radius, so I'm trying to think why you can't just immediately jump to a circle of radius 1. So we would get f of z over z is less than equal to 1 divided by r. Why would this be the case? Oh, now I remember, okay.
Well, if r is less than 1, then 1 over r is going to be bigger than 1.
Yep.
We're mapping to the disk, so.
Okay, so z,
Oh,
the absolute value of z is equal to r. Why do I have a 1 up there?
Because f is
Because I'm mapping to the disk. Mapping f from d to d implies f of z is strictly less than 1 in fact. Now I remember why the book wants to do a circle of radius r. We've got to be a little bit careful because we're only mapping the interior of the disk to the interior of the disk. If I immediately went to a circle of radius 1, my function is not necessarily defined on the boundary of the unit circle. Right? Yes?
When you keep talking about the interior of the disk, do you mean you're including the boundary?
No, I'm not including the boundary. Whenever I say interior, I'm emphasizing that the boundary is not included. So
But
D,
when you're just saying the unit disk.
the unit disk for me does not include the boundary. So I sometimes try to emphasize this by saying the interior. But it's actually from the Department of Redundancy department. There's no need to say the interior of the unit disk. It's just the unit disk. But I want to emphasize that I'm not including the boundary. And we do not know that our function is defined on the boundary of the unit circle. So I can't just say absolute value of z equals 1. I have to do this annoying extra step of going through z is on a circle of radius r. So this implies that the absolute value of f of z is less than equal to z over r for any r in 0, 1. And now what can I do? Now that I'll approach to 1. Now send r to 1. And the minus sign here means we're sending it to 1 from below. So as we go all the way up to 1, this does imply that f of z is less than equal to z in absolute value. And so this is the proof of the first part of Schwartz. Okay? So there was a little technical subtlety or complication here. We can't just jump to the boundary of the unit circle because our function might not be defined there. In calculus, whenever you talk about derivatives, it's always the derivative on an open set. You want to be able to move in a small neighborhood about the point. And so if we're on the boundary of the unit circle, we may not be able to move in a neighborhood. Okay, so this is Schwartz 1. So what we want to do now is Schwartz 2, is that if there's some point where f of z and f of z naught and z naught have the same absolute value, then it has to be a rotation. Has everybody copied this down? Okay. I want to keep the statement of Schwartz on the board, but unfortunately we do not have a good amount of blackboard space in this class. Either that or I'm too pedantic. Okay, Schwartz 2. So assume there exists a z naught 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 such that f of z naught in absolute value is z naught. What kind of contradiction are we going to get? What does it mean if f of z naught is the same as z naught in absolute value? Yeah.
You can get from one point to the other via rotation plane.
Right. So I mean, we know that they differ by rotation, but I want to get some stronger consequences. So remember, we were looking at the function f of z over z before. And we used that to show that f of z is less than or equal to z in absolute value.
Is there like a one-to-one kind of calculation? Or?
Not a one-to-one. So remember, we were studying g of z, which was f of z over z. And what do you know about this function?
It's zero, it's zero.
It's 0? Well, we don't know that
Well,
actually.
we don't know that, but
You know something about this function because you know something about all holomorphic functions.
They have their maximum on the boundary.
They have their max on boundary. What would it mean if you had a maximum in the interior?
It's uniformly one.
More than uniformly bounded.
Constant.
It's constant. And so the reason is, if interior max, that implies it's constant. And so, I'll draw, hopefully a nice proof by picture. Here's a circle of radius 1. Here's a point z0. And I'll take a slightly larger circle of radius r. So inside the circle of radius r, I have the point z0. I know the maximum is on the boundary. I've just attained a maximum also at an interior point. But holomorphic functions map open sets to open sets. So if I look at the function g of z0, that's mapped to that's mapped to 1 here. So if I look at a small neighborhood about z0, that's got to be mapped to a neighborhood about 1. Oh, if it's mapped to a neighborhood about 1, I found a point where the value of my function g is now greater than 1, contradiction. So essentially, open mapping principle, max modulus principle, they all come into play here to tell us this can't happen. The only way it can happen is if the function is constant. So what this means is it means f of z equals c times z. Okay, what can you deduce about the value of this constant? I'm sorry?
It's the 1 minus 1.
It has magnitude 1.
It has magnitude 1, right? The absolute value of c has to be 1 because we can plug in the point z0. As the absolute value of f of z0 equals z0, which does not equal 0. Okay? That should come into the proof somewhere. Right? This is not equal to 0. That implies c is 1 in absolute value. Okay? So c has to be 1 in absolute value. If z0 was allowed to be 0, then notice I wouldn't be able to conclude anything about c. Right? So it's really important that in the Schwarz Lemma we say z0 is not equal to 0. If you want to think a little bit back to your proof of like the mean value theorem, where you get the existence of an interior point, where the first derivative at that interior point is equal to the average slope. You don't want the point to be at the endpoints, you want a nice interior point where the behavior is happening. Alright, so we know the absolute value of c equals 1. So, as the absolute value of c equals 1, that implies I can write c as e to the I theta. Because when I write my complex number in polar coordinates, or in polar form, the radius has to be 1 so that it has magnitude 1. And that's a rotation. So, thus, f is a rotation. Okay, 2 down, 1 to go.
Can you say go one more time how we got from there's an interior max, which is a contradiction.
Sure.
So
So if there's an interior max, if you look at what happens when I apply g,
well, how do we know that there's an interior max? I guess.
well, I've got some point z0 that's inside the unit disk.
Sure.
So let's take a circle of radius r, where r is larger than z naught in absolute value.
Okay.
So f of z naught over z naught equals 1. But we know the maximum value of f of z over z is 1 in absolute value.
Oh, I see.
So we've now shown that, the maximum has to occur on the boundary, it's occurred on the interior as well. Because I have an open map, if I look at the image under G, so here's the point 1. So if I take G, G of z naught is sent to 1. So a small neighborhood about z naught has to be sent to a neighborhood about 1. So in particular, if this is the origin of the complex plane, I guess I should draw it over here. So we don't know exactly what the phase of G is. We only know its absolute value is 1. So let's say it's sent over here. If I now just continue and move in that direction, I get a larger value. So this is, again, very strange properties of complex analytic functions. So the fact that an open set is mapped to an open set gives us great control over what's going on. If I move a little bit more in that direction, there's some direction I can move about z naught, I will get a larger value. And if I have a larger value, I've now contradicted the fact that the maximum is on the boundary. If you think back to Calc 3, which for those of you who haven't taken the juries recently might be hard, how do you find the maximum values of a multivariable function? So you do the derivative for the interior points, and then what do you do for the boundary?
Check all the boundaries.
You check all the boundaries. So a lot of times, what can you do to check the boundary quickly?
Divided into parts.
Not divide into parts.
Reason.
So somebody mispronounced Euler's name at Math Puzzle Night last night. And I said there are two names in math that you cannot mispronounce. Euler. And in fact, for the physicists, you should be able to figure out who the other one is, because this other one is often hyphenated with Euler and occurs frequently in Calc 3. Lagrange. Right? Don't say Lagrange.
You love it.
Right. Euler Lagrange. Yeah. Just painful to hear. Okay? But then you have Lagrange multipliers. And Lagrange multipliers tells you how do you find maxima on boundaries. How do you find extreme points? And you have this really nice condition. But it's not necessarily the case that extrema occur on the boundaries. For real variable functions, a lot of times the extrema occur in the interior. Complex holomorphic functions are very different. You only have to check the boundary. The only way you can win inside is if the function's constant. Right, if the function's constant, it doesn't really matter too much what you do. Okay, are we okay now with Schwartz 2? Alright, can I erase this? Schwartz 3. So there are two different ways of proving, there's at least two different ways of proving Schwartz 3. Okay, so Schwartz 3, you must show the absolute value of f prime of 0 is less than or equal to 1 if equals 1, then a rotation. You can easily make this an if and only if. If it's a rotation, it's not hard to show that the absolute value is 1. Okay. So, I will give the book's proof first. So again, the goal is not to see how quickly we can go through complex analysis. If people want to have one class like that, I'm game. I want to try to emphasize how you should attack problems like this. What the hell should we study? Okay? So, there's a very natural quantity to study. And we've been looking at this quantity all along. What quantity have we been studying again and again and again with Schwartz? F of z over z. So we've been studying g of z is f of z over z. I claim there's another way of writing f of z over z.
Minus u.
I'm sorry?
F of c minus u over c.
Okay, so it's f of z minus what?
0?
I don't want to write it as 0.
Yeah, well, 1 0.
Thank you. Minus f of 0 over z minus 0. So I claim that for this problem, this is a far better thing to look at. It looks like the derivative. You know, it's a limit away from being the derivative. What are we trying to study in this part of the Schwarz Lemma? The derivative. Right? So we know for any choice of z, this is equal to g of z. And what do we know about the magnitude of g of z? It's less than or equal to 1 in absolute value. So if we take the limit as z goes to 0 of f of z minus f of 0 over z minus 0, and we can take absolute values of that, this is less than or equal to the limit as z goes to 0 of g of z over z. And for all z, what do we know about g of z over z? I'm sorry? Oh, no, sorry, not just g of z, thank you. And what do we know about the absolute value of g of z? Less than or equal to 1. My function is differentiable, so this is just f prime of 0 is less than or equal to 1. Yes. That's half of Schwartz 3. What's left now? So what would it mean if it equals 1? Okay. So assume f prime of 0 equals 1 in absolute value. Okay. What can we deduce? What function do we think it looks like?
E to the I theta.
Times z.
Times z.
So we think it's basically just a rotation. That's what it's claiming. So if f prime of 0 equals 1, we want to show somehow that this forces our function f of z to just be z. Or better yet, z times a number of absolute value 1. So how would we get that? So we've got f prime of 0 is equal to 1. Okay, what would you want to integrate? I'm sorry? I would say a trivial thing to integrate, not a dumb thing. Because that's just a constant. So we somehow want to get from the fact that f prime of 0 equals 1 to the fact that now g of z is constant. So there's a couple of ways to do this. There is the way in the book. So if you've read and digested the book, that is one approach. Since that approach has made such a lasting impact on you, I will not complete this as the book does. I will leave that as an exercise for you to read the book, and I will show you another way to do this problem, which will really roll up your sleeves. Okay? Okay, but I promise, no algebra, just analysis. Okay? They're just short. They can be rolled up a little bit. There you go. Okay. What do we know about a function? So I've given you a holomorphic function. What do you think of as soon as you know you have a holomorphic function?
Has a primitive.
It has a primitive. What else? has a Taylor series expansion, right? These are the two things we know, right?
No.
No, I told you you're going to roll up your sleeves for this one, okay?
Yeah, let's do it.
All right. And this is why we have you submit that. Okay.
Not on camera.
So we know we have a Taylor series expansion. So what I want to do is I want to explore what can we deduce from the Taylor series expansion of F. So a couple of days ago in the notes, I think I said we didn't get to too much material today, so I'm going to throw in an alternate proof of the open mapping theorem using the analyticity of the function. So I will try to put back a link to that today if you want to see more of what can you do with Taylor series expansions. So F has a Taylor series. So I can write f of z. What's the zeroth order term in the Taylor? Zero. So it's going to be a1z plus a2z squared plus dot 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 dot. So I claim if a1 is 0, we have trouble. Let me just make sure I'm seeing the Schwarz. In the statement of the Schwarz lemma, can someone just check in the book to make sure it doesn't say we want an onto map, that we just want an into map? I just want to make sure I'm not putting in an extra assumption. Yes. So it's just the opposite value of f prime of 0 is less than or equal to 1.
Yeah, you're good.
Okay. Alright, so we want to study what's going on. So there's several ways to go. So if we're willing to take what we've already done, we know f prime is at most 1. And so all we have to do is then study what's going on if f prime is equal to 1. So claim. Already showed f prime of 0 is less equal to 1 in absolute value. So let's assume f prime of 0 equals e to the I theta. Because that's the difficult cases. We want to show that this implies that a function is a rotation. Okay? So now we have f of z is e to the I theta z plus a2 z squared plus dot 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 dot. Okay? So so what do you see is going to happen?
So you take the absolute value and use triangle inequality to show that it's going to be less than or equal to 1 because the maximum modulus. Then the latter part is going to be 0. So it has to be e to the I theta times z.
Alright, so say that again.
So you take the absolute value.
Of which? The left-hand side or the right? Okay, the right-hand side?
Yeah.
Okay.
So that's less than or equal to like triangle inequality.
The sum of the different pieces.
Right. Then you
But that inequality is going to go the wrong way. Because then this will give us something that's greater than 1 in absolute value. And this will just be trivially true.
But then f has to be bounded by 1.
We know it, we definitely want to use f as bounded by 1. But if I use the triangle inequality, then this piece has length 1. This will have a positive piece, and this will bound f by something greater than 1. But that's okay. If f is at most 1 in absolute value, it's also at most 1.2 in absolute value.
But can't we say f of z is less than or equal to absolute value of e I theta z plus a squared z plus whatever, which is less than or equal to 1? Because the value of f of z has to be less than or equal to 1.
Okay.
So then you just squeezed it into 1.
So what we want to do is we want to basically say somehow that if a2, a3, and a4, if they're not all 0, there's some choice of z where this is now larger than 1 in absolute value. That's essentially what you're saying, is we want to somehow show there's a choice of z. Well, if you look at what's going on, a3 z cubed plus dot 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 dot. If z is really small, the magnitude of this piece beats the magnitude of this piece if a2 is not 0. So, if a2 is not 0, a2z squared is greater than a3z cubed plus dot 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 if z is not 0. And z is small. So if you take z really, really small, this series converges. And it has an extra power of z than a2z squared. So I can choose z to be so small that the contribution from this is strictly less than the contribution from this piece. I'm almost done. I need this thing to now be larger than 1 in absolute value when I take the derivative. So f prime of z would be e to the I theta plus 2a2z plus 3a3z squared plus dot 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 dot. Okay, so I do the same argument as before, and I can show this whole thing is going to be less than this thing if I wanted. You can argue either, I think, either with the derivative or with the function. We know the derivative is less than 1 in absolute value. Here's something of absolute value 1. What do I need to do to make sure that this plus this is larger than 1 in absolute value? We're almost there. So let's give this a number. Let's call this, what's the easiest number to think of that's 1 in absolute value? 1. What would you like this number to be so that this sum is definitely greater than 1 in absolute value?
Positive real.
Positive real. So you want this number to be in the same direction as this number. That tells you what direction you want to take z. I choose z such that 2a2z is in the same direction as e to the I theta. And now this will be greater than 1, and it'll be greater than 1 by enough so that this can't overtake it. So align 2a2 of z with e to the I theta. And now you've got the absolute value of that special z is going to be greater than 1 in absolute value. And that's a contradiction. Alright, so let's go through it again. So when we take the derivative of the Taylor series, I'm assuming the second coefficient is not 0. And we'll show that that's a contradiction. The same argument implies the third, then the fourth, then the fifth. All the a's have to be 0 after the first. Well, my series still converges when I take the derivative. We can now review, if you have a power series, you can differentiate term by term within the radius of convergence. Because it converges, and this has an extra z over this, if z is sufficiently small, the magnitude of this piece over here is less than the magnitude of this piece here. So I can say, for instance, if z is really small, this is at most half the magnitude of that. I now choose z to align so that 2a2z is in the same direction as e to the I theta. And so if you want to figure out exactly how you do that, if you write a2 as rho e to the I phi, you would let z be some r times e to the I theta minus phi. And that would tell you exactly how to align things. And so what I can do is I can now make sure I give myself a little bit of a boost in just the right direction. So this is a very different proof than what's in the book. I happen to really enjoy proofs like this. I really like taking Taylor series and seeing what I can milk from them. We've been kind of discriminating, I think, in this class. And I've got to be careful because I've actually just been emailing yesterday Professor Stein, one of the two authors of our textbook, about something. And I love the textbook. I keep having publishers telling me they want to switch, and I really like a lot of things about the book. But one of the things that is worth emphasizing a little bit more is the other perspective. Is what perspective do you have from the analytic series? Sometimes we use it, sometimes we don't. It's extremely powerful to know you have a series expansion. Now, this finishes the proof of all of Schwartz. So Schwartz is now done. Now the only thing is, we did use the book's proof to show that f prime was at most 1. Can we do that without using the book? Can we argue just directly from Taylor series expansions? So let's go back to this line. We know that the absolute value of f is less than or equal to the absolute value of z. And they have equality if and only if they're rotation. So imagine the first derivative was not less than or equal to 1. could we somehow get a contradiction? So this number would now be greater than 1. And we could make the exact same argument. So I think we have like 1 minute left. I don't know if we have half a minute left. So since we only have half a minute, I'll just write it very, very fast. If we have f of z is az plus a2z squared plus dot 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 dot, if this number is greater than 1 in absolute value, I'm going to have a problem. I can make this so small that it's still going to be greater than the absolute value of z. So you can actually use this to completely avoid all of the arguments from the book.